So to start, in a function named display, we printed out each index of the board in a 3 by 3 layout and separated them with two vars to separate the columns and multiple dashes to simulate the rows.
In the main method, we said that while the win condition was false, we played the game with the computer and checked if tie or win condition occurred. When it occurred, we broke the loop and printed who lost, who won, or who tied.
We also had to check if any players won so that the game ended if either the computer or the players had three in a row. For this, we used various if statements for each situation, such as vertical, horizontal, or diagonal, and iterated through each row 3 times and checked if there was three in a row of X or O that occurred. We also had a small check tie function to make sure that no one had won and there's no open spaces on the board.
Next, we needed the computer to go first so that it can have a better position at winning. For the computer's turn, we implemented the minimax search algorithm. We looped through all the empty indexes of the array and temporarily moved the computer there, since we don't want the whole board to be filled with the same move. Then we called the minimax function, which I'll get into later, which simply recursively loops through all of the possible moves by the computer in the current state of the board, and then simulates all the possible moves done by the user. Its end goal is to maximize its own points when the user is trying to minimize its points, and it runs recursively until there is a terminal state or a state where the game is won, lost, or tied. Then it returns a number 1, -1, or 0, and for each move of the original state, it assesses the highest number between all the moves, which is how it determines which place it wants to move.
We also needed a user to move so that the computer points are minimized after each play. We took the user's input for two coordinates, the x and y, and separated them by a space. To create a point on the 2D array that would correspond to their move, we also had to check if the inputs were valid moves, like if there were actual numbers, or if they were within the limits of the board size from like 1 to 3. If both conditions are met, then we place the move on the board and call the display function. If not, then we recursively called the user function again and made the user enter it once more.
Finally, we have the minimax function, which we explained briefly before. The minimax algorithm can be implemented in many different ways, but essentially comes down to using the same recursive methods. It typically takes a depth argument and a player argument. The depth keeps track of how far it moves in the program, and the player argument lets the algorithm know which player is being maximized, minimized at a specific state. First, we had to define conditions for which the program would stop. If the computer won, return 1. If the user won, return -1. If it tied, return 0. Then we can continue by defining two conditions. If the computer, which we decided to define as the number 1, is currently playing during the state, set a variable to -infinity and loop through the board. We temporarily replaced each empty move with an x and then assigned the previous variable to a math.max function, which replaced the variable with the highest number between the recursive minimax function and the maximum value. This will allow the computer to know which moves after a certain depth are the most effective for that one initial move in the initial state. The recursive function called will increase depth by 1 and set the player to the opposite player, which in this case is the user, or 0.
Then we also had an else statement that alternated the conditional to if the player was the user. This time we did everything listed before that the computer did, but we replaced the max with the minimum between the min and the recursive function minimax, which added to the depth and set the alternating player as the computer. This is because the user is trying to minimize the computer's move, so the less the user's points are in a particular move in a state, the more likely the computer is to not move there. And this is the else statement.